Hello everyone, welcome to k-mer analysis with Python. This is the second video in the series, and today we are going to be counting k-mers from raw data that I just downloaded from NCBI. So we have here two files. It's from a Salmonella phage, and I choose those because they are very small, so it's going to fit in my computer memory, and also it's not going to take long for doing the counting. And then, of course, you also need a library here. It's called MMH. So make sure that you install it like this. And then you can start doing the counting. All right, I will start by reading the files. So I'm going to take those as an argument of our program. So argv in the position 1, it's going to be the first read file, and in the position 2, it's going to be the read2 file. Then we need something to store our k-mers. It's going to be kind of a global variable in this namespace. It's going to be called k-mer storage. It's a dictionary. And we can call a function that's going to process the read file, and we give the read file as parameter. We can also do the same for the second part. And the last thing we need to do is to generate the coverage of frequency. And this is going to be important so we can run the output, the final output, against the plot file that we wrote in the previous video. All right, we don't have the functions here, so we needed to create the first one, process file. It gets a file path, maybe a read file as parameter. In this particular case, it's a decompressed file, but let's make it hack here. So we do custom open equals gzip.open if read file ends with gz, otherwise else we go with the regular open. Okay, we also need now to import gzip over here. And this means that if we give to the script a fastq or a fastq.gz, it's going to open in both cases. So with custom open, we give the read file and we say that we're opening it in read mode and in text mode as file handler. And then we can start iterating over the lines. Also, it's important that we look the format of a fastq file. So we have the header, we have the sequence itself, a separator, and the quality score. These 4 lines will repeat over and over again in this file. So the first line is going to be a header, and then the second line is supposed to be the sequence. So we can ask for the next line here. The third line is going to be the separator. We call next again on the file handler, and last line is going to be the quality. This is a hack that we can use to iterate in batches of lines. So we are iterating every time over 4 lines, the lines that represent a single record from the fastq. Then, of course, we only need to work with the sequence. So we can assign the sequence here to this new variable, and we can also remove break lines, so new lines character. The next thing we need to do is actually count the k-mers from the sequence. We can actually go and print it and run it once just to see what's happening. So if you run the count.py and you provide those read files, that's what you get. Only the sequence part of the files. So now we can do the counting. So count k-mer, and let's say k-mers, and we needed to provide the sequence, and we can also say that we want k-mers of size 21. Again, we don't have the function, so we need to create it. So count k-mers, and it's going to expect the sequence and the k-mer size. All right, next thing, we get the size of the sequence. So len sequence, and for I in range. So we get the size now, the k-mer size that we want to look for, and +1 over here. So this is just to make sure that we don't try to count k-mers that are smaller than 21 when we arrive at the end of the sequence. So right here, we look first at 21, then 21, 21, and we keep doing it. And once we hit the last 21 k-mers, we don't try and go to read like 20 or 19 or 10. So this is what we're doing over here. We make sure that the range is going to be the length of the sequence minus the k-mer size +1 because Python is 0 base indexed. Okay, we're going to say that the k-mer that we're reading is the forward one, and we're going to get the sequence in the position I plus k size. I'm sorry, position I to I plus k size. So we started 0 to 21. And then we go to 1, 2 to 22. And we keep doing that until we arrive the last 21 nucleotides in the sequence. Okay, so now here we have the k-mers. We can take also the reverse of the k-mer. And for that, we need to write a function that we're going to call reverse complement. And we give the forward k-mer as parameter. Again, we don't have the function, so we need to define it, reverse complement, and we are giving a k-mer. And now we need to make sure that we translate the k-mer that we have to the complement. So we can use just basic Python here and create a rule that's going to be make trans from the Python library, the string library. And we say that for every time that we find a, C, G, or T, we are going to translate it to T, G, G and C, and T and A. Okay, yes, that looks right. And then we can return the k-mer, translate it. So we translate it using the rule that we just created. And then, of course, we got it in the reverse format. So it becomes the reverse complement. Okay, so now we have the forward and the reverse. And now we need to pick just one. We don't need to put variations of the k-mers. And then, of course, in the raw data, sometimes the read is going to be in one direction or in another direction. And we need to make sure that we only pick k-mers in one direction. And for doing that, we can use the min function. So it's going to take the smallest one, and we can say forward k-mer and reverse k-mer. This may be a little bit counterintuitive, but it should work like this. So you can have a Unicode code for each one of the nucleotides, and then you can see that it can become a list, and you can run the min over two lists. So let's say we have the k-mer A, C, G, and T, and the k-mer T, G, C, and A. Doesn't matter it starts as forward or reverse. Once we provide this to the min, it's always going to take the smallest one and should be A, C, G, and T. So T, G, C, and A never will be counted as a k-mer, only the reverse complement. So this ensures that we get only the smallest one. And then we need to hash it. And this is mostly to save memory. So mmh3.hash, and we give it to k-mer, and to say that we wanted a signed integer as a hash. So now every time that you get, let's say like this k-mer, it's actually going to be an integer. And of course, integers cost a lot less memory than strings inside the Python dictionary that we're going to use to store the k-mers. All right, next step, we need to take our k-mer storage, and we say that k-mer hash is going to be the key. And we try firstly to increment this count. But if it's the first time that we're seeing this key, so it's the first time that this k-mer, one of the versions of the k-mer, either the forwards or reverse, appears in our file, we can actually start the counting. So we register the k-mer hash and we give it a value of 1. The last thing we need to do is to write the generate coverage frequency. And then again, the function doesn't exist, so we generate coverage frequency. Because the k-mers are already counted here. And it should be very simple. We create a new dictionary here, coverage frequency, and we say default dict. So this variable is a dictionary that has default value as an integer. And for k-mer and coverage, in k-mer storage.idents, we can do coverage frequency gets the coverage plus 1. So every time we see this particular coverage, doesn't matter from which k-mer, so we are just counting coverages now, we increase 1 for this particular coverage. Lastly, we can make the coverage frequency again. It's going to be a dictionary of sorted coverage frequency based on the idents inside of it. So we're just making sure that we are ordering this coverage frequency dictionary from the biggest value to the smallest value. And then we can say we open a file here. We're going to call it genome.histo. And we need to be able to write through this file. So as file handler, and then for coverage and frequency, in coverage frequency.idents, we can make a new line in this file and should be an F string where we put the coverage here, so C, and we give a space, and now we put the frequency, and of course you need to make a new line here, and it is done. So if I didn't write anything wrong here, it should generate the same output that you get from Jellyfish that we saw in the first video. So let's cross our fingers and run it to see how it's going to behave. We are going to call Python and then the count.py, and we provide both files and we run it. So this should take a couple of minutes. I will forward the video so we can see the results. All right, it is done. It worked, no failures. You can see here that we have the genome histo file. We can actually go here and take a look. It looks exactly like the Jellyfish output. And we can make sure that it works by running our plot script from the previous video. So Python plot.py genome.histo. And it says here that it found the start of the Poisson distribution at position 38 and the end at position 213. The coverage peak is around 110, and the genome size estimated for this phage is 163,000 base pairs. And this is the plot generated by the script. So we did the counting, and you can see that it works. We got a kind of goodish Poisson distribution, and we estimate the size of the genome, and I did run an assembly of this genome, and in fact, this is the size that we get. A few considerations here. This code is not very optimized, so it works fast here because it's a very small file, so it's just a minute or a minute and a half to do the counting. But if you try to run this against real-life Illumina data, or let's say a bacteria, for example, with a large coverage, like a file with hundreds of megabytes or maybe gigabytes, this algorithm here is going to be very, very inefficient. And mostly because Python is not very efficient itself. So you are going to need a lot of memory, and it's going to consume a lot of time. The idea I'm trying to sell here is that don't use this code to count k-mers from raw data. It should be fine for doing this to count k-mers from a genome, but from raw data, it's not going to be very pretty. Okay, see you next time.